Thank you very much. Luke Steels would probably describe me as an ancient logical positivist in the awful tradition of Reichenbach and all those people. Actually, I realize my talk is probably a bit out of place, but I tried to convince you, probably I won't, but I'll have a go at trying to convince you that there's still some life left in old logical positivism, particularly since people like John McCarthy and Richard Montague and many others in the 1960s really made a revolution in logic by making it apply to common sense reasoning, apply to natural language processing and knowledge representation and so forth. So I think, although there's a bit of logical positivism in my approach, I think that logic itself has really moved with the times, and I don't see a big contradiction with the kind of approach that Luke talked about this morning. Just a bit of very quick background. So here, examples are that in ontologies and taxonomies, and in fact in any kind of knowledge-based system, you can often represent some piece of knowledge in using different languages or different vocabularies. And the same is true for mathematical models that we use for modeling natural or social phenomena, for doing simulations, for representing common sense knowledge, or even for representing the knowledge of a software agent at a certain moment in time. So for example, in machine, these are there's a couple of very trivial examples I mentioned here, but in machine learning or planning, it's sometimes useful to split a predicate which has n arguments into several smaller predicates. So for example, instead of having an expression like move an item X from Y to Z at a certain time I, you could actually have three different predicates to do this for you. One to tell you that X is an object, that it's moving to Y, and that there's a destination Z at time I. And this is actually known as operator splitting, introduced by Kautz and Selman in a famous paper. In causal action theories, one sometimes makes use of what are called action attribute symbols. There's a famous problem of missionaries and cannibals, as you probably know, crossing the river. And instead of saying that a vessel V is crossing in a certain location, we might actually split this up into two different predicates or relations. And I'm missing some reason a little bit at the bottom of the slide. These changes of language are not just purely aesthetic. In fact, operator splitting is used to speed up search. And Lifshitz made use of action attributes to improve elaboration tolerance. So he has like many variations of McCartney's cannibals and missionaries problem. And the idea is, can you change the problem without having to redesign your whole program or package that you use to describe and reason about this problem? So these are just there are many other examples. If you think of 8 puzzles on a board, then you can think of the tiles on the board as the main object that's moving, or you can think of the tiles as being static, and you move the rows and columns of the board. So you can have dual representations of many problems. And so one of the things I'm interested in is how to capture equivalence of meaning or synonymy when you're using different languages. And I want this to be applicable to different kinds of computational knowledge bases and knowledge representation formalisms. And I want to illustrate how it can apply in one very popular area, which is called answer set programming. I can't really go into all the details of answer set programming. But I'd like to see, if there's time, we'll see if it generates any interesting problems for the future that might relate to some of the work you're doing in essence. Let me give you some background assumptions. So I'm going to assume, and I can't defend them all in such a short time, I'm going to assume that meaning is grounded in knowledge, and that the locus of meaning is a theory. But a theory, informally, is something very general. It's a body of knowledge that is explicitly reconstructed in some system. And formally, I want to think of it as a set of sentences in some language that's already equipped with the precise semantics. Okay, so I'm not trying to discover semantics, I'm assuming that there is a semantics. I also want to assume that the semantics is model theoretic, but this is not so restrictive. It doesn't have to be classical models. They can be Kripke models, they can be Boolean valued models, they can be lattice valued models, they can be almost anything you like. And although I said a theory is a set of sentences, I like to be able to handle things like programs, schemas from databases, data structures of other kinds that are used to encode knowledge. Okay. Okay, there's a bit of the slide that's missing. There's one restrictive assumption, which is that I'll assume that the different languages share the same underlying logic. But we can see how we might try to relax this assumption at a later stage. Some very old related work. The theory of interpretability in logic started from the late 40s and early 50s, mainly through the work of Tarski and his followers. And thanks to this theory, we had very important results in logic, like the undecidability of group theory, for example. In the beginning of the 60s, there was treatment of synonymy in logic, and some names are mentioned there. And I started to work in the 80s on applying these concepts to knowledge, reconstructions of scientific knowledge, basically. In non-classical logic and in formalisms for knowledge representation, things are not so well developed. So there's quite a lot known about some relevant non-classical logics and some of the important theorems they have. But in the context of knowledge representation formalisms, it's only fairly recently that people have studied different types of equivalence you might have between programs, between theories, between different kinds of knowledge bases. And most of this work has not yet extended to the case where your knowledge or your theories are formulated in different languages. So the methodological message is to try to suggest some desiderata or criteria of adequacy for a concept of synonymy for theories in different languages. Okay, and there are six parts to this. So the first one is that you want to be able to translate. So I'm assuming I've got a language L1, I've got a theory Pi1 in that language, and I'm going to be able to translate from the language of Pi1 into the language of Pi2. Then I want to have a semantic correspondence. I've assumed that we have some semantic structures, that we understand the language is interpreted. And now I want to map now in the reverse direction, because if I'm translating from L1 into L2, then I want to map my L2 models into my L1 models. And this mapping should preserve so the translation was Tor. Okay, Tor was the translation. And now I want my mapping F to appropriately associate with that Tor. Okay, so a formula will be true in the image of the model if its translation was true in the original model. Here's a very vague and obvious condition. I want my theories to be equivalent under translation in an obvious sense, but I have to make this precise for different cases. Okay, so I can only give you examples. This is a very important condition. When we reconstruct any kind of knowledge. It can be scientific knowledge, or it can be some problem situation that we reconstruct in some AI formalism. Then not all the models will correspond to the real world in some sense. So not all the models of a scientific theory will be, when it's formalized, will be actually represent empirical things in the world. And not all models of our representation of cannibals and missionaries will actually refer to the real solutions we want to our cannibals and missionaries problem. So whatever we mean by intended model, and this again will depend on the formalism, we want those things to correspond to each other. Since we want synonymy to be essentially an equivalence relation, it should have a symmetry property. So if pi1 maps to pi2 and they are synonymous, then we want to be able to say that pi2 maps to pi1 in the same way. And finally, there's another condition which we need when we leave the realm of classical logic, which is, now I lost a bit of slide, I call it robustness. What this means is that if our two theories are equivalent or synonymous under some correspondences, then when I add something to one of the theories, then this addition plus the original theory should be synonymous with the second theory, with pi2, let's say, and the translation of the sigma, right? So this is not obvious when you leave classical logic and monotonic inference. Okay, so we get different kinds of relations when we specify more particularly what those correspondences amount to. I mentioned, or I hope maybe I mentioned, answer set programming is the area where I show you very briefly how we can apply these ideas by using a theory of interpretations. Answer set programming is a popular formalism. It's a declarative logic style of programming formalism, but it has many interesting features. It's of non-determinism. You can reason about defaults. You can reason about preferences. You have aggregates, and you can use it to represent causal action theories. You can use it for planning, and there's many applications coming up all the time. It's not a commercial product, but there are several very efficient implementations of it. And the semantics is based on what are called stable models. So you have logic programs, and the semantics are, the models, the intended models are called answer sets or stable models. And they are what represents the solution to your problems, okay, in answer set programming. And in order to apply these ideas to this type of AI formalism, we need to do two important things. One is we need to represent these programs that you have in answer set programming. We need to represent them linguistically as formulas of a certain language, and we need to cope with the fact that inference is not monotonic in answer set programming, because we have defaults and so on, defeasible reasoning. And it turns out that there's a base logic we can use which will do these things for us, and this logic has some nice properties. So we can, so if we're dealing with answer set with non-monotonicity in the form of answer set programming, then we can use, there's a logic called here and there. I explain very briefly what it's about, that we can use as the base case. And there's a logic which we worked on for many years called equilibrium logic, which exactly captures these answer sets or stable models in a logical format. And I skip these slides about the here and there logic. The only thing you really need to know, or the only thing may be useful to know, is that in this logic, in the propositional case, everything works for first order logic, but I just show you the propositional case. You have two sets of atoms, H and T. So H is here and T is there. And what they mean is that H represents what's true, definitely, and T represents what's not false, the atomic propositions that are not false. So things that are in T are not in H. I like to think of them as true by default. Okay? If something's not in T, then it's false. Okay? So it's essentially a three-valued logic. Okay? But it's also a logic that extends intuitionistic logic, so you can use Kripke models too. And very simple Kripke models. We just have two worlds here and there. So I don't go into the semantics of this, but just mention that if you take a rule of a logic program in answer set programming style, which looks like a formula at the top, where you have a head of the rule on the left, which is a disjunction of atoms, and on the right you have a conjunction of atoms and negated atoms, and you simply transform this trivially into a formula with not an implication and so on, and then your stable models, your answer sets, are simply a particular kind of model in this here and there logic. Okay. So, how do we do translatability in this format? So, I'll just mention a predicate P or an atomic proposition P is definable in a theory if there's a formula phi that's equivalent to it in the theory, and explicitly, and it's implicitly definable if whenever I have two models of the language that contains this predicate or this atomic formula, and and those models have the same agree on everything except for this extra predicate or atom P, then they are actually equal. That means this is when P is implicitly definable. And there's a famous property in logic which says that if you're lucky, your logic has the Beth property, which tells you that things are implicitly definable if and only if they're explicitly definable. So actually, not all. Some of the logics people use in ontologies, for example, don't have this property. So, what's an interpretation between languages is simply a recursive translation that satisfies these obvious properties, and it induces a mapping between models. So that in the mapping between models, so F is the map between models, and W refers to the world H or T within the model, because now it's not a classical model we're talking about. It's a three-valued thing, and then we can derive this second property that phi is true in the image of the map F if its translation is true in the model you start with. And now, what does it mean to interpret one theory in another? Well, I can interpret pi1 in pi2 if every theorem of pi1 transforms into a theorem of pi2. So the picture is, if you like, is on the right. So you have, in the big square, you have all the L2 structures, all the models for L2. And then the smaller square, or rectangle, is the part of L2 which corresponds to what you've translated from L1, okay? And then you have the pi2 models, and among the pi2 models, you have all the translation of pi1. Okay, so that's a basic interpretation, which already preserves a lot of interesting properties. Now, in addition, a translation is said to be faithful if this implication is an if and only if it reverses. So something is a theorem of pi1 if and only if its translation is a theorem of pi2. So the picture then looks like in the bottom. So the translation of pi2 covers everything of pi1 that is expressed in the language that translates L1 into pi2. So how do we get synonymy? Well, the first thing we need is an interpretation, and this takes the models of pi 2 and the models of pi 1. The second thing we need is that this semantic mapping is an injection, and that it's faithful. Okay, so these are the three things that constitute a synonymy relation, and then we call, if we have those three properties, then we call it a bijective interpretation. Then this means that we can translate from one theory to the other and back, and we always preserve all the theorems. So how does this then work in a context like, I lost a bit of slide, a context, what's the equivalence under translation? Well, what does it mean to say that they are equivalent under translation? Well, actually what happens is that from pi 2 you can infer the translation of pi 1, but it doesn't mean that pi 2 and its translation of pi 1 are equivalent in L2. Okay, so they might not be equivalent because the translation of pi 1 need not be as strong as pi 2. Okay. However, you get some nice features. For example, if you add all the definitions to pi 2 of terms from pi 1, and you add all the definitions of terms from pi 1 in pi 2, then you get extensions of the theories which really are logically equivalent. Okay, so this means they have a common definitional extension. And they respect, in this case, we respect the intended models of the stable models, and we can prove that these are respected, and we also have a robustness condition. Okay, I even lost a bit of slide, so I don't give you the condition, but it's exactly what I mentioned before. In the first order case, it's exactly the same, a little bit more tricky technically, because we can have different individual constants, function symbols, and so forth. And in this case, we each, in an interpretation, each predicate of one language then has a translation into the other language. So I said I'd close with some research challenges. So one is, what's new with respect to things like semantic alignment? Well, the bottom line is that, if you can read it, yes, that in formalisms like ASP, we don't have classical logic, we don't have monotonic inference, and so there's a whole set of new issues that are raised. And there's lots of problems that you can express in ASP that you wouldn't want to try to express in classical description logics, unless you add a lot of new features to them. What if meanings are not determined only by theories? Well, my answer to this is that it's very difficult to separate meaning from knowledge, because if an agent uses concepts in the right way, then he or she or it must have some knowledge about how to use those concepts. So, and this is the famous, related to the famous problem of analyticity. So it's difficult to know how concepts can be acquired without knowledge of use. And but even if you want to say, and some people sometimes do say, that something like in reconstructing ontologies, a T-box represents the meanings of concepts, right? Whereas an A-box represents things that are true in the world, perhaps. Well, that's no problem. Then let's work directly with the T-boxes, and then we'll be mapping those. And the synonymy idea doesn't really change very much. Another thing we can look at is how to generalize these kind of definitions, which are very simple. In more general cases, you will have perhaps a predicate of one language in one variable may correspond to a predicate in n variables in the other language. Okay, so the semantic correlation, and we may have correlation between models that have different domains. Okay? So in the very simple case, they'll have the same domain, but in more complex cases, the domain will change as well. And it remains to be seen how these more general kinds of definitions and translations can be accommodated in formalisms like ASP. There's let me just only mention the fact that you can combine rules in answer set programming style with ontologies in description logic style, and these produce hybrid theories, and there are stable model semantics for these things, and you can also talk about equivalence. But though we know a bit about how to deal with equivalence, to deal with equivalence between systems in different languages is still, let's say, an open research issue. And the final one is to mention that what happens if our underlying logics are different? Well, if we use the idea of a common definitional extension, then in principle there's nothing to stop us supposing that this definitional extension uses a combination of two logics, okay, not only a combination of two vocabularies. So one way to go would be to use work on combining logics. Another way to go is to look at work done in AI in the 90s on translating between different knowledge representation formalisms. But most of this work was to look at the different expressive power of formalisms. It wasn't to translate between languages. So adding translation between languages would be to add a new feature to that kind of work. So I'm done. Sorry if I went a bit too long.
Thanks very much.
I knew it. It was just too much out of, yeah.
I have a question. So there are, I mean, in this space of trying to look at kind of different theories and how to relate to each other, there are very different approaches. There is, the kind of model logic approach. There is some people do it with category theory. There are, some approaches.
God forbid. God forbid. Category theory.
What do you think is a promising avenue to, if one wanted to move from the modeling part to implementation and to actually help agents kind of somehow use some of these mappings kind of practically, or in order to relate them to, let's say, algorithms or ontology mapping or whatever? In your experience, where should one look?
Well, since I like ASP is actually quite good at sort of programming itself. I mean, you can extend the language and then compile everything back into ASP. So a lot of the work we do is adding new types of reasoning capabilities to the basic language. And in fact, there's no reason why you couldn't use, since it's already very expressive as a language, you could certainly use it to try to characterize these relations, not just mathematically, but actually programmably. And but there hasn't been much done on that yet. So, but that's just because I like this kind of language. But and I'm too old to learn category theory. So no, I think the thing is I don't. Category theory is very rich mathematically, but I'm not sure that it really helps when you come to more practical. I mean, you're interested in very practical questions and I think in the end you like to have systems that you can program easily and that look reasonable. I mean, maybe this all looks very complicated, but I can assure you it's very simple, because if I can do it, it means it must be extremely simple. So, but it's not designed. There's no learning mechanism attached to this to actually discover these relations. You have to sort of guess them, and then if you guess them, I think you can program them in things like ASP. It should be quite good. Oh, I wish it would. I'd love to be able to help you, but I don't think so. I think what it's supposed to be able to do is to tell you that if you start splitting some predicates or redesigning your representation, it should give you a handle on how to check eventually that you haven't changed the problem, if you didn't want to change the problem, right? So assuming that you don't want to change the problem, but you want to have maybe a nicer representation, then it should be able to tell you that what you've done is equivalent, but it won't. I don't think it'll help you to find it. I think you have to have some ideas on how to do that yourself.